Hello everybody. We're still talking about the kinetic reactors in Aspen Plus, and we will see the CSTR by solving this example here. So this is kind of a simple example where we have a reaction of acetic acid with ethanol giving ethyl acetate and water. We mentioned this reaction before in the ideal reactors, but here we are going to solve the same reaction by knowing the kinetics of the reaction. And we usually, or we were doing this reaction in a CSTR because it's a liquid phase reaction under atmospheric pressure, and the reflux temperature, which is going to be mentioned here, I think somewhere here. The kinetics is power law kinetics with K1 equals this number, and we know the K2 and the activation energies. And it's mentioned here, this is important, that this is a first order reaction with respect to each one of the reactants in both directions. This means that the reaction is first order with respect to ethanol and acetic acid in the forward direction, and first order with respect to water, and first order with respect to ethyl acetate in the backward direction. So just to be like aware of what we're gonna do, we're gonna consider this as two reactions, not just one reaction. The first reaction is the forward reaction, and the second is the backward reaction, and each one is gonna be defined separately. And that's why it's first order with respect to the reactants in the forward direction, and first order with respect to each one of the reactants in the forward direction, and first order with respect to each one of the reactants in the backward direction. And we want to know if the volume of the reactor is 140 liters, what's going to be the volume of the conversion of the reaction. We know some information about the feed, the temperature, the pressure, the flow rate of the inputs. I have here, I'm gonna put them side by side so that we see everything, or we have all the information available when we need them. Just one point here, that mentioning that it's first order with respect to each one of reactants in both directions. So it's gonna be like this. This is for the forward direction. There is one for the backward direction that I didn't mention here, but this is how it's gonna look like. It's gonna be K forward, C acetic acid power 1, and C ethanol power 1. This is power 1 for each one of them. So it's first order with respect to each one of the reaction. This is what it means. Let's first go for the first part of the defining the file. It's gonna be the defining the components, and I have already defined them: ethanol, acetic acid, ethyl acetate, and water. And by the way, there is a very common mistake here that makes a lot of problems, which is putting dots here. So if you put dot in acetic acid, it's gonna make a lot of problems later. So in case you need to put some spacing between the letters, you cannot put space, but you cannot put dash. So please do not put spaces, do not put underscores, do not put dots, do not put anything like that. So I have all the components defined here, and it's clear that I have water, alcohol, acetic acid, so they are all polar components. So I kind of know that I'm gonna go for an activity coefficient model, but again, for some reason, I wanna go for the method assistant. It's component type, it's a chemical system. And it's not at high pressure. And again, like what we did last time, it's gonna suggest the NRTL when an activity coefficient model like an RTL Wilson, whatever. But here we have here a carboxylic acid, which is acetic acid. So in such case, you have to use an activity coefficient method with any one of these models for vapor phase associated, such as like in RTL HOC or NTH. So this just to deal correctly with the acids, the carboxylic acids that we have. And it mentions here that organic acids such as acetic acid form dimers in the vapor phase and require a special model to account for non-ideal phase behavior. Just for the non-ideality, we have to do or take into account that by using the NRTL NTH model. So this is all for the properties environment. Now we go to the simulation environment. I've already defined all the feed parameter that we have, the flow rates, and I have the temperature, the pressure, which are here, the temperature 75, the pressure 1 atmosphere, and 160, 11, 570, and 8, 600, and everything is fine now. Now let's go for the block itself, which is the reactor. I'm gonna go for an RCSTR, which is rigorous continuous stir tank reactor with rate control reaction. So this is what I'm gonna use. Connect this here and connect the output here. And you see you can have here, which is different from the PFR, you can have more than one input and more than one output. In the PFR, you can have only one input. So this gives you more flexibility than the PFR. And here we will call this as the product, and this is gonna be called CSTR. And now we need to explore this unit and see what we have here. So we have to define the operating conditions. It was mentioned that it is at the feed conditions, if I remember right. It is the atmospheric pressure and the same feed temperature. So it's gonna be at 75 degrees Celsius. We're gonna work in liquid phase because I'm using the components at a temperature which is below the boiling points of all of them or most of them. Or in case you want to make it vapor liquid, you can do that. Then you can specify the something related to the reactor itself, either the volume, the residence time, and residence time, which is the flow rate divided by the volume. So I mean the volume divided by the flow rate. So you can have that. You can define the reactor volume and phase volume, and in this case, you know you have two phases, and you define how much of the reactor volume is occupied by the vapor or how much is occupied by the liquid, or you can define it as volume fraction instead of just volume. You can define the phase residence time. So all these options will be valid in case of having more than one phase. But in my case, I know I'm gonna be working with one phase, and I know the volume is 140 liters. So this is already specified. The gain the streams is like in the case of the PFR, is we're gonna use this to define which phase is gonna go into which stream. So in case of having multi phases and multi product streams, we will use this tab. We will keep the reactions later. The PSD, again, it's for the particle size distribution in case of having a catalyst. Again, this is when using solid phase. I think this is what we use it for. Utility, we mentioned it before, in case you have cooling water or heating medium, so you can choose which utility that you are using. Again, for the catalyst, in case of having catalyst, you can define the loading and the voidage and all these things. So the part that we need to go into details about is the reactions. So I don't have any reaction sets defined here, so I'm gonna define one new reaction set. I'm gonna call it R1, and the type is gonna be power law kinetics. And it's gonna take us here to the reactions the same way we did in the previous case or the previous video when we dealt with the PFR. So I need to define a new reaction here. So as I mentioned before, we will have two reactions. We consider this as a separate reaction, and this is another reaction, the forward and the backward reaction. So for the forward reaction, it is ethanol and acetic acid, and the coefficients of each one of them is -1. And the exponent here it's first order with respect to each one of them, so it's going to be 1 and 1. For the product, it's going to be ethyl acetate and water. The coefficients are 1 and 1, and the exponent is 0 for each one of them because it is not function of the rates or the compositions of the products of the reaction. And this is what's mentioned here. It is first order reaction with respect to each one of the reactants of both direction. So this is what we're gonna do. Now we can define a new reaction here, which is reaction number 2. And in this reaction, it's gonna be the opposite. It's ethyl acetate and water. The coefficients are 1, it's -1 here, -1 here, the exponents are 1, and it's going to be exactly the opposite, and the product is ethanol and acetic acid. The coefficients are 1 and 1, the exponents are zeros. I think I didn't put the 0 here in the exponent. So this is all what I need to do to define the reaction. So I define this reaction and I define this part, which is the C power 1 and C power 1. So I just need to define this K according to the Arrhenius form of the reaction rate. So I'm gonna go for the kinetics. I have here 2 reactions. What I have here is valid for 3, 4, 5, whatever the number of reactions that you have. So the K is, but just keep in mind that you have more than one reaction, so you have to make sure that you are putting the values for the right reaction. So this is the forward reaction, which is ethanol plus acetic acid. So the K is 1.9 10 multiplied by 10 power 8. The activation energy is 5.95 E7. But again, the critical part here is the unit, so it has to be kilojoule. It's joule per kilomole, so it's important to pick the right units, because it's gonna make a lot of error if you choose a different unit. And here it says that the base of the concentration is molarity, so you can use it as molarity or molality or mole fraction, mass fraction, partial pressure, whatever. So I'm gonna go for molarity because this is how the kinetics are based on. So the first reaction is done. Now let's go for the second reaction. It is 5 E7 and the activation energy is 5.95, 10 per 7. This is joule per kilomole. So now the reactions are totally defined and the CSTR is totally defined. So we don't need this anymore. So we can run the simulation and see what kind of results that we're gonna get out of this. It's now processing, and sometimes it takes some time before it generates the results in the first time. So now we have the results here, and we can see in the results here that there are not as much results as we have before. So there was a tab in the PFR that's called profiles, and we had a lot of outputs from this profiles tab, but in this case we don't have any one of these. We have here some heat duty, and the duty is because the reaction is kept at specific temperature. We didn't mention anything about having a different temperature or about the duty, so it's assuming that it's an adiabatic it's isothermal reaction, so we have some heat that is kind of absorbed from the reaction because it's a negative. The volume, we have it, the vapor phase, there is no vapor phase, so it's liquid phase as I expected. And there is the residence time, and the residence time is again the time that the components spend in the reactor going through the reaction. So it's kind of 1/3 of a minute almost, so it's very short time. Back to the results, I'm sorry, there are not many things that you can have out of here. Again, the summary is gonna be almost the same thing and put in different way. Not much information. So for the stream results, we can get information about the composition of the product and the conversion. So the feed is 186.67, which is the number of moles of the limiting reactant, and the product is 120 moles. So we have almost 60 or more than 60% conversion. And this is kind of expected in case of having reversible reaction, because you will never reach 100% conversion. One thing that we can do just to test the reaction and see how we can kind of see the effect of the parameters that we have. So we can change the reactor volume from 140 to make it 1000, for instance. And by doing this, we are giving the reactants more time to react, and this would result in more conversion. So by doing this, we see that the mole fraction or mole flow is 123 instead of 120. So it's increasing, but not much. We increase the volume a lot, like 6, 7, or 8 times, and we didn't see that much increase in the conversion. So it means that we are getting closer to the equilibrium conversion. So for instance, if I make it 2000, so I'm doubling it now, and by doing the run and back to the stream results, we'll see that it's not that much changes, 123. So it seemed that it reached the maximum conversion. Um, you can kind of play with it just to find the equilibrium conversion, or to know how much or the maximum conversion that you can reach. And you can test the effect of temperature. You can test the effect of many parameters if you are interested. And this is something that we can do using the sensitivity analysis that we mentioned before. And it's going to be a good exercise that we can do in the next video, inshallah. So I'll see you then. Goodbye.